Compressors. Let's take a look at the shape and the guts and the insides of a compressor. Everybody knows that the intake of a jet engine is where the air goes in, but what's behind it? Some spinning compressor blades. Okay, all the diagrams, they show jet engines as a bunch of fans spinning around in quite a few spaces. Pretty simple, one big piece moving, a few things not moving. Seems pretty simple. There's the intake of a turbojet, and we're going to take a closer look at the compressor and the stators to see just what kind of spaces exist in there. Okay, let's take a look at another compressor rotor. Okay, tucked in amongst all the other stuff in the shop, this is the compressor rotor of an LM1500 J79. This is the back end of it. The intake end is right here facing the floor. That's what the air first encounters, these blades. You can see the spaces between the rows, and those match up with the stators in the case. And where does that rotor fit? And what does it work with? Well, we have one set of cases right here. Let's take a look. This is the matching compressor casing from an LM1500. And inside all these stators is where the wheels of the compressor turn. You can see there's not any extra space for things like birds and gum wrappers to fly through. So over there's the compressor rotor, and it fits right in here, and it's very tight. There is no room for anything else except for the compressor rotor inside these cases. The diagrams that we see don't show every stage of stator. There's a stage of stators behind every stage of the compressor rotor. Each of the stages of the compressor rotor matches up with one of these slots, except for this one. Now, we've covered this in a previous video, a couple years ago actually. These are called the outlet guide vanes. They're a form of compressor stator, but because they're the last thing that the air sees before leaving the compressor, they're called outlet guide vanes. You could call these stator guide vanes, but they're usually called stator vanes. Outlet guide vanes. This is a two-piece design. There's no rotor stage in there. The 17th stage of the rotor's here, and the air contacts this stage, or sub-stage I guess, and then this one to be directed straight back into the diffuser, which we covered recently. I like the way it looks with a case half off. Pop the hood, so to speak. Yeah. Look at that. Look at all the stators lining up with the... Now, compressors, axial compressors anyway, they're all different. They come in all different shapes and sizes, but they all are kind of the same. Let's take a look at a little tiny one from a 1400 horsepower engine we had in here last week. Look at this little guy. Well, there is a medium-size gas turbine engine compressor. Let's see, what engine is that out of?
Solar Saturn.
Solar Saturn. How much horsepower?
This one, 1400.
1400 horsepower.
Yeah.
Cool. Can I have it?
Yes, it's yours.
And let's take a look at these. They're a bit loose. This is normal. This is the way they should be. So there's no real resonance. They don't ring like a tuning fork like some of the other rotor blades in other videos. Those, actually we'll take a look at those right now. Here we are outside with our cutaway. This is the exact same thing we were just looking at. This is an LM1500 J79 rotor, and what's different about these blades is they're all rusted solid into their wheel. They're corroded and full of dirt right down there in their mounting, so that they're solid. This is a very dangerous situation if this would be a running engine, because they'd probably start to ring and vibrate and crack. But this is our cutaway model, and that's the sound of dirt trapped down in there. You can see there's the matching of the compressor rotor and the stators. Well, look, we're missing some stators right there. Anyway, that's how closely it matches up, and you can see which parts move and which parts don't move. Those are the passages through which the air must pass to be compressed. Okay, so it should be quite obvious that anything that goes in there has no chance of surviving. Okay, we're out here in the graveyard of turbine engines with a turbine-powered helicopter in the distance to look at how does a compressor blade wear out. There's two examples on this one right here. This is a stage 1 blade from an LM 1500, and let's see if we can get in there real close. Okay, we're moving in here to the blade root right along there. This is the surface that bears the centrifugal load of the spinning compressor rotor, and I hope you can see there's some wear. This blade, on inspection from removal of an engine, was decided there's too much wear there, so we junked it. There's another very good example of what happens. This can't be repaired. What can be repaired, up to a limit. This is the leading edge of the compressor rotor blade. And you see that rough texture with all the little pits and holes and moon-like surface? You see that leading edge? All the pock marks from tiny particles of solid debris, sand or dust, smashing into that at very high speed. This is a solid stainless steel blade, so you can get an idea of the energy and the speed of this thing. 7,200, 7,400 RPM. To repair this, all this would have to be filed away and then repolished to a nice smooth leading edge of the airfoil. This one could be fixed, but because of the root wear, we junked it. This is why intake air filtration is so important for an industrial turbine engine. They run for much longer periods of time between maintenance than an aircraft engine. Once again, thanks for watching.